Last time we started the proof that this differential form, which is a 4 form, is a total derivative, which means that it is the exterior derivative of this 3 form, which is, however, defined only locally. It does not depend on the coordinates, but it depends on the frame, the Lorentz frame on the tangent bundle, which we may start calling Lorentz bundle. So basically, if you work out its variation, even an infinitesimal variation, under local Lorentz transformation, which follows from the infinitesimal variation of the spin connection, it will not be zero. We have not done, and we will not do this exercise, but if you want, you can check it or you can find it in books. The curiosity is that the variation of C is again exact locally, is again D of something, the exterior form. So this doesn't mean that this form is exact, because C is not globally defined, and it does not mean, using Stokes' theorem, as a consequence, that the integral of this is zero. It depends on, even if the boundary of the manifold M is zero, or the manifold M is non-compact and the metric decreases sufficiently fast, rapidly at infinity. This is not necessarily zero, and it is normally a topological quantity. And in 2 dimensions, we have said that it is the Euler characteristic, and it is an integer that counts the number of holes of Riemann surfaces. Those surfaces are closed. Okay, I don't find the surfaces here, but you remember that. There's a Riemann surface. So a Riemann surface is something like this. And its Euler characteristics is 2 minus 2g, where g is the number of handles or holes. So in 4 dimensions, we had to do some calculations. And so we manipulated this expression, and we isolated a certain thing, which is a total derivative, and 2 other contributions. The third one was proved to be zero. And now we consider the second one, which will also be a total derivative, and it will be the total derivative of the second contribution to the Chern-Simons form. So it will be the total derivative of that. So the first contribution, you see, is the total derivative of the first contribution to the Chern-Simons form, precisely this one, epsilon omega d omega. Epsilon omega d omega. And the second one now we see. So let us work out this with the 2. Yes, we'll keep the 2 for convenience. We do not need the integral because it's an identity that doesn't need the integral sign. And we want to prove that this is precisely 2/3 of d of the other thing. Now we will check. This was omega AB, omega CG, omega GD, epsilon ABCD. Here it is, 2/3 omega AB, omega CG, omega GD, epsilon ABCD. So I want to prove that. Well, let us work out this exterior derivative. So we have 2/3 d omega AB, this is the first contribution, omega CG, omega GD, epsilon ABCD. And then we have the derivative here, which has to cross one form, so there will be a minus sign, and then there will be a derivative there. And as you may imagine, as usual, those two give the same contributions, which is easy to prove because they have one contracted index and then they have C and D. So when you exchange the two, you have a minus from the commutation of the one forms, and you have a minus from the rearrangement of the indexes C and D, of the indices C and D in epsilon. So the two give the same contribution. So we write the D on the first one. So we have minus 4/3 omega AB d omega CG omega GD epsilon ABCD. So the first one is okay, is the one we have there, multiplied by 2/3, and it will be enough to prove that the second one is the same thing with minus 1/4. So again, to be proved, this thing is well, no need to write it down. It's, we can do it directly. We just do it, and we'll see. So omega AB. Now, instead of writing d omega CG, we write d omega CG as the following way: minus 1/4 d omega PQ epsilon PQ MN epsilon MN CG. Let me raise the indices. And then we have G downstairs, D epsilon ABCD. So it's the usual trick. I insert two epsilon tensors with two indices that are contracted, and therefore that gives minus 2 delta PG delta QG delta PC delta QG minus the thing that you obtain by anti-symmetrizing in P and Q. So you have minus 4 of that, which cancels the minus 1/4 and gives exactly what you have on the left-hand side. And now we proceed as before, because we have two epsilons with one contracted index, and we can evaluate them by means of the determinant of delta tensors. So minus 1/4 omega AB d omega PQ omega GD. There is one epsilon that will remain. We will write it. And then the contraction of those two. They have C both on the third, in the third place, so no minus sign for that. But there is a minus sign because we are in Minkowski space, so the epsilon tensor, when it gets contracted, generates a minus sign. And now we copy the indices. M and G. And ABD. Okay. As usual, this will be, instead of 6 contributions, just 3, because every one of the 3 will contribute twice. Let's see if there is anything that disappears. No, I don't think so. So we have to do them all. And we can, for example, do it here, because if we leave out the columns with m and n, we will have twice as a doubling. So delta AG is the first one, it's the third column, so we have minus 1 over 4 omega AB d omega PQ delta AG, which means A here, d epsilon PQ. So if we are doing this, we have MB ND. Twice, because we have this delta MB delta ND minus delta NB delta MD. So twice. Then we have delta GB. Oh yes, there is one contribution that disappears, by the way, the third one, delta GD. Delta GD will contract the indices G and D, and remember that we are using the metric compatibility, so the spin connection is anti-symmetric. Which means that the third contribution is not there. And the other one is delta GB, but delta GB, due to the anti-symmetry with respect to A and B, and the minus sign cancels, it gives the same contribution actually, so it's very easy. Minus 4 divided by 4. So it's minus omega AB d omega PQ omega AD and epsilon PQBD. It's very similar to that. It's very similar to this. Let's just check that it's equal. It should be equal because this minus takes care of this minus sign. So if these two are actually equal, 2/3 plus 4/3 is equal to 2. So we just have to prove that this is that. And that is true, or what? Let's see. So we have minus. Let me exchange the d omega PQ with omega AB, because d omega is a 2 form, so I can exchange it. And then we will have to rearrange these indices a little bit. So first I copy them, and then we will rearrange them. Epsilon PQBD. So d omega has two indices that are contracted with the first two indices of the epsilon tensor. That's fine. Then we find omega omega with the first and fourth indices, which are equal to those B and D. So B and D. But here we have to exchange one index. So if we exchange one index, we have a problem because the minus sign should survive here, and it doesn't. So we check it again. No, it's okay actually. It's okay. So when we exchange those two, BA, we lose the minus sign, which is correct because what I wrote here, although it is not apparent because so what I wrote here was this omega AB, etc., without the minus sign. No, we have to check it. because what I wrote here is without this minus sign. So if it is equal to plus the other one, we would have 2/3 minus 4/3, which is minus 2/3 instead of 2. I mean, the conclusion would be the same, but the Chern-Simons form would not be the right one, so we have to check it. Chern-Simons form has a unique form, which can be derived in many other ways, so we have to be careful. Anyway, let's check again. Omega AB d omega CG and omega G d epsilon ABCD. I can check it here. Yes. So minus 1/4, which appears to be right. See, yes. And then we have two epsilon tensors. Okay, so minus 1/4 omega d omega GD. The two epsilon tensors must be contracted. Oh, yes, I inserted a minus sign. You didn't tell me. This is the third line, so it doesn't have a minus sign, an extra minus sign. So for example, delta GA, this was a plus, so this is a plus. There is no, it's the third line. So, and therefore, here we have a minus. Yes. Omega AB, once we switch those two, we have a minus. And then we have exactly that form. Yes. So this is the proof. Now, what is the use of this Chern-Simons form? In the Chern-Simons form can be used in 3 dimensions, actually. Because if you consider the integral on the manifold of M, this is an invariant. Invariant under Lorentz transformations and diffeomorphism. Diffeomorphisms because it is a form, Lorentz transformations because it works like that. It's a little bit long to check in the case of gravity, so we will check it. And since it's not very important for this course, we will check it in the case of electromagnetism, where it is easy. Under Lorentz transformations, local Lorentz transformations, infinitesimal ones, delta theta is d of something. You can prove that it is the variation under Lorentz, infinitesimal Lorentz transformations, even global Lorentz transformations actually, of this form is d of something. And that something is well defined as a form. So this is really an exact thing. And so the variation of Lorentz transformations of that integral, not the integrand is not invariant, but the integral is invariant. So since it is a little bit long out of the purposes of this course, let's do it in a simple case, because if you will meet the Chern-Simons form, you will mostly meet it not in gravity, but in QED, sort of QED, which is called Chern-Simons QED actually. It's not really an electrodynamics. There's not much dynamics in this theory. It's called a topological theory. So let's start from d equals 4, where you may consider the integral of f wedge f, and f is equal to dA, and that is equal to 1/2 d mu a nu f mu nu. We know that. And so this object can be written as 1 divided by 4. Those two forms will be writable like this, f p nu f rho sigma, and then you have dx mu, dx nu, dx rho, dx sigma. And I recall that dx mu, dx nu, dx rho, dx sigma is equal to epsilon mu nu rho sigma d4x. So here you can write epsilon mu nu rho sigma d4x. This is the invariant E dot H using the electric field and the magnetic field. It's not the Lagrangian. The Lagrangian is E squared minus H squared, and that is f mu nu squared, f mu nu. So this is a little peculiar. Well, you can write this also as d mu a nu d rho a sigma epsilon mu nu rho sigma. And then you can check that this is a total derivative, because you can also write it as d mu c mu, where c mu is this. So let me write what c mu is. So c mu is this, epsilon mu nu rho sigma a nu d rho a sigma. Now, if you go down from d equals 4 to d equals 3, you can consider this object. Take the 0th component. The 0th component is epsilon 0 nu rho sigma a nu d rho a sigma, but now nu, rho, and sigma are all space indices, ijk. So you can instead consider this object epsilon ijk ai d partial j ak. And that is the object you can consider in 3 dimensions. This sort of action, which is the Chern-Simons action, which has completely analogous properties. It's simpler, however, so we can study them much more easily. For example, if you take this integrand, it is not gauge invariant. Let me check. Gauge invariance is this symmetry. Okay. And the integrand, which is epsilon ijk ai partial j ak, is not invariant, because it is equal to epsilon ijk. So when I apply the variation to ai, I obtain partial I lambda. And when I apply the variation to AK, I obtain partial A, partial K lambda. This thing is 0 because there are two derivatives on it, partial J and partial K, and there is an epsilon that kills them, so that is not important. Now, observe that this thing I wrote here is itself a total derivative, because I can write it as partial I, epsilon ijk, because partial I, when it acts on there, together with a partial j, again, because of the epsilon, gives 0. And what remains inside can be written not just in terms of the connection, but in terms of the field strength. So the variation is really exact, because it's the total derivative of something that is gauge invariant. So it's defined throughout the manifold, so this is non-zero, but the variation of the integral of that now will be 0. That's why you can consider this as an action. Because as an action, it is really invariant. Even if the manifold is compact. If the manifold is not compact, you do not really need this to be gauge invariant, but you still need it to decrease sufficiently. We will see some example later. In gravity precisely, because we will have to use this property in the case of gravity. Symmetry property. So we have studied the quadratic corrections to the action, and we have listed the invariants that we can write. We have studied several combinations. We have still one to list. It's not an invariant. It's a rearrangement of those same three invariants, and it involves a new kind of tensor, which is quite important, so it has to be considered. That is the Weil tensor. Basically, the Weil tensor is the Riemann tensor to which we subtract all the traces. It's denoted by W or C, capital C. W mu naught sigma is the Riemann tensor plus, in d dimensions, that it exists in all dimensions, and we will comment on properties in different dimensions. We have R mu sigma G nu rho. You just subtract the traces, so there is not much you can write. There are two terms that you can write with just the right coefficients in front. Since this is anti-symmetric in mu and nu and rho sigma, when you write something like that, you have to make it anti-symmetric in mu, nu, and rho and sigma. So let's just do it. So, sometimes you have many indices, many terms to write, but they are, you know what they are, so they are block-wise, they are really simple. But unfortunately, gravity is like that, and you have to deal with this. And then there's another term which will turn out to be multiplied by this object, d minus 1, d minus 2, which is R. And what can you multiply it by? G mu rho G nu sigma minus G mu sigma G nu rho. So again, there is not much else you can do. You have just two coefficients in front, and you just choose those coefficients in order to have 0. So for example, if we compute this thing, which means set mu equal to nu, that will be 0 by itself because everything is antisymmetric in mu and mu, so this we do not need to do. But if we, the only thing we have to do is equating mu to rho. So let me write mu here. If you equate mu and rho, the first one will be Ricci, mu sigma, and then you will have 1 divided by d minus 2, whatever. What do we get here? If nu is equal to rho here, G nu rho is d. So you have d r, oh sorry, if mu is equal to rho, here you just have r nu sigma. If mu is equal to rho, this is mu rho. Now, if mu is equal to rho, you have G mu rho, so this is d r nu sigma, where d is the dimension. Let me call it n, not d, because d is the derivative, exterior derivative. And so you have minus n. The third term with mu equal rho gives the Ricci scalar. And the fourth term with mu equal rho gives again r nu sigma. So you see that n minus 2 goes away. Too quickly, actually. Yes, it goes away, but we have a third term, which I cancel. Why? I don't understand. Yes, so good. Plus 1 divided by n minus 1, n minus 2, r. So when mu is equal to rho, that is n, G nu sigma. And when mu is equal to rho, that is 1 G nu sigma. G nu sigma. And so you see that this is 0 because here you have 2 minus n that cancels n minus 2, and you have r nu sigma minus r nu sigma. Which means that this, and this cancel. And I have the terms with r are multiplied by G nu sigma, and here in front you have minus 1 divided by n minus 2. And here you have n minus 1 divided by n minus 1 and minus 2, so plus 1 divided by n minus 2. Therefore you have 0. So this is an interesting tensor that cannot be introduced in terms of differential forms. Actually, that is how you introduce it, but it has a very interesting property. First of all, it has symmetry properties, which are the same of the Riemann tensor. W mu nu rho sigma is equal to minus W nu mu rho sigma, and that is equal to W rho sigma mu nu. Then you have a Bianchi identity. So if you cyclically permute the three indices, the last three, and you keep the one first fixed, you have 0. And you sum, you have 0. Nu rho sigma, so you have nu rho sigma, nu rho sigma. That is 0. Then there is another identity, which is another way of which is well, it is what it is. Don't know how to call it. Self-duality, double self-duality. W mu nu rho sigma is equal to minus 1/4 epsilon mu nu alpha beta epsilon rho sigma gamma delta W alpha beta gamma delta. Actually, no, I cannot write it this way. Careful here. Careful. Cannot write it this way. Have to resort to flat space indices. Why? Somebody can tell me why. What's wrong in writing something like this? Is this a tensor? Well, this is a tensor because it's a Riemann tensor with raised indices, but the question is this a tensor? And this is not. The epsilon tensor is a pseudo-tensor actually, and so there are some square roots of G around, while in flat space indices, epsilon A, B, C, D is a tensor in flat space indices. Epsilon mu nu rho sigma is not. Since we have not said this so far, we have used epsilon mu nu rho sigma sometimes, maybe not too often. It's worth to pause a moment on this. This is not a tensor. Why? Well, if you want an invariant, we know, for example, the cosmological term, that is what it is. But we also know that dx mu, dx nu, so let's try this, to write this in terms of differential forms. We know that this is epsilon mu nu rho sigma d for x. So, one thing you can do is multiply everything here by epsilon mu nu rho sigma with lower indices. And then what do you get? You get epsilon mu nu rho sigma dx mu dx nu dx rho dx sigma, that is equal to 2 epsilons, which is minus 24, d4x. So let me write this square root of minus g times d4x. I just replace d4x with minus 1 over 24, that. Now we see it as a differential form. This differential form has these components. So this is a tensor. And indeed, what you obtain is something that transforms correctly. So square root of minus g epsilon mu nu rho sigma is a tensor. Because they are components of it collects the components of the volume 4. Similarly, epsilon mu nu rho sigma is a tensor if you raise the indices, because this is what you normally defined like this: epsilon 1, 2, 3 equal 1, and then the rest. This is a number. And the two things are the same, the two statements are actually the same statements, because it's obvious that you can write epsilon mu nu rho sigma as g mu alpha, g nu beta, g rho gamma, g sigma delta, epsilon with raised indices, alpha, beta, gamma, delta. So if one is a tensor, the other one cannot be a tensor, because if this is made of numbers, this is a matrix that knows about the space-time point. But fortunately, you can cancel all those four by putting just a square root of minus g, and then you get a tensor. So you can have both, obviously, because now when you raise and lower indices, you have to use the metric, while here, with flat space indices, you use the flat space metric, and that doesn't disturb you. So both are tensors. Now, let's see if we have time. The Weil tensor is very important because it has a very special symmetry property. And it is invariant, in a certain sense, under what we can call Weil transformations. which may also be called local conformal transformations, conformal invariance. And this is the following invariance. G mu nu, the metric, is rescaled everywhere by means of a certain rescaling factor that may depend on the point. So they are local because the metric, the distances, are redefined with a scale factor that depends on the space-time point, depends on the location that you consider. And it so happens that the Weil tensor is invariant if you write it this way. With 1 index up and 3 indices down. Again, it's not the same because the difference between this one and the one with all 4 indices down is a metric, and the metric is not invariant. So the Weil tensor written here is not invariant. It will transform, however, in a nice way, very similar to the metric. But the one that is invariant, and this is a little bit long to check, but we will not do it here. But this one is invariant. And this property allows you to build a particular combination of quadratic terms that is conformal invariant. And it's a particular action that is completely conformal invariant. You can write it this way. So let me, it's W squared. So you contract mu with alpha, you contract nu with beta, rho with gamma, and sigma with delta. And then this is invariant. Why? Because this is invariant, these two are invariant. The metric takes a e to the minus 2 omega. So this takes e to the minus 2 omega. Those are inverse matrices, so they take this factor, each, because they are inverse, the inverse of the metric. And then you have square root of minus g, but g is the determinant of g mu nu. And so it's the product of 4. Oh, by the way, this is only true in 4 dimensions. So, that's right, in 4 dimensions only. Okay? And so the determinant in 4 dimensions picks 4 times that factor, e to the minus 8 omega, and the square root of the determinant picks e to the minus 4, which cancels exactly those minus 2 plus 2 plus 2 plus 2 equal 4 omegas. And that is a very, very special situation. Similarly, the Yang-Mills action is conformal invariant in 4 dimensions, because f mu nu doesn't know anything about the metric, and so here you have e to the 2 omega, e to the 2 omega as before, and square root of minus g is e to the minus 4 omega. So you may wonder if this symmetry is so special to guide us to write theories and actions. Well, not so much, because apparently nature does not like it. And there is no evidence in nature of a conformal symmetry. Actually, nature is very different from small distances to large distances. But in special cases, fixed points of the renormalization group flow, if you heard about it, it may be useful. Then you can have limiting situations where this symmetry is interesting, not particularly with gravity, however. Anyway, it's important to know that this action exists. It's a very, from the physical point of view, it's a very bad theory, because really you cannot make much sense out of this, not even classically, let alone at the quantum level. But it's interesting because of this symmetry and some applications. So let's stop here.